So, this week's lecture, we're almost at the end of the module. It's gone very fast. You may currently have a view that all these interesting problems around uncomputability and incompleteness, they may appear interesting and fun and novel, but not very relevant to the real world problem that you are trying to solve and getting paid usually to solve. This week I wanted to talk about how these problems become amplified and spill out into the real world. What you tend to find with logic is that you only need one little problem somewhere and you can very quickly create large infinite classes of variations on that problem. And some of those variations are going to spill out into the kind of problems that you might actually be working with in real life. So this is especially the case around numbers. When we try to define what is meant by a number and what is meant by arithmetic, almost everything we do in our day-to-day computing lives involves some arithmetic. And there are fundamental limitations that get placed on what we can do with numbers and arithmetic that are a direct consequence of uncomputability. So by studying this, we can learn how to avoid attempting to do things that are impossible and wasting our time, and we can also get ideas for how to represent numbers in different, better ways that are less likely to lead to errors. So in particular, it's common practice to use floating point data representations, as we talked about in computer architectures, and that there are well-known problems with floating point. When you have numbers that are very big and very small and you combine them in certain ways, it can horribly blow up. Sometimes literally, it can blow up rockets and aeroplanes if your floating point arithmetic goes wrong. So there are other ways to represent numbers which don't have those problems, but they bring their own limitations, and that's most of what I wanted to study today. So this lecture is called Uncomputability Everywhere, and it's about taking these ideas into everyday number systems and other problems in programming and metaprogramming. So I'm going to go back to Turing's paper, which was called On Computable Numbers, if you remember. Turing's 1936 paper isn't about computers, it's about numbers. We're going to go back and look specifically at the numerical focus of that paper and see what Turing really did and why it is so great. We'll talk about how you can do arithmetic on these kinds of numbers. We'll talk about the size of this set of numbers. And then in the second half of the lecture, we'll look at what that means for limitations, which problems to do with numbers and programs are uncomputable, and how we can get by in a world that is filled with an infinity of these small uncomputable problems everywhere. Okay, so what did Turing actually do in 1936? Okay, this paper is called On Computable Numbers, and the purpose of it is not to define the computer, but it is to define numbers, or it is specifically to define a particular set of numbers which are arguably interesting and useful. So far we have talked about various number systems. We started with the natural numbers in computer architecture, for example. We went to integers, so a big letter N for naturals. Naturals start at 1 and keep going. Integers, big letter Z, they can be negative as well as positive. We've come across rational numbers written by a big letter Q, which are fractions. A rational number can always be written as A divided by B. So for example, 1/3 is a rational number. So is 10.5. This is just a different way of writing 10 and a half, which you can find numbers a over b to write as another rational. There are other kinds of numbers which we need to talk about sometimes. So we saw last week a proof that root 2, the square root of the number 2, is not a rational number. You can never find a and b to write root 2 in that form. So root 2 is something else, but we still need to talk about root 2 and have it in our number system. Other numbers which are irrational but useful include e. This is the mathematical number e, and the mathematical number pi. So these are called irrational numbers. They cannot be written in rational form, but they are well defined. We know exactly what they are. We can write down precise equations, but they have endless decimal or binary expansion. So we call these infinite precision numbers. They're numbers that just keep on going, but in a well-defined way that we can understand. So Turing wanted to redefine the number system in a way that includes all of these numbers and includes any other number that is actually useful, any other number that can be defined and constructed in a way that it can be put to work and do something useful. This is not the same thing as what mathematicians had previously been doing. So before Turing, the mathematicians invented a much larger set of numbers, which they called real numbers, written as R. So I'm going to use T for Turing to mean the set of computable reals, because no one's ever bothered to define a standard symbol for it otherwise. So the mathematicians have their own purposes. Turing was half mathematician and half engineer, and he was concerned about stuff that actually works and does useful things in the world, whereas pure mathematicians generally aren't. They're concerned with making things that are pretty and interesting. So there are many more numbers in the mathematician's set of real numbers than there are in Turing's computable numbers. But it will turn out that all the extra numbers the mathematicians talk about are literally useless. They're impossible to describe, they're impossible to do anything with, they're impossible to use, hence useless. And the mathematician's definition was very contrived. People still worry about how it handles these different kinds of infinities and so on. Turing's definition is different from that, and it's better than the mathematician's definition because it gives you a well-defined constructible set of numbers that are all useful, and it doesn't include any crud that isn't useful. So we will begin by studying what these numbers are, how they're defined. Then we'll look at how we can do arithmetic on them, and then we'll look at the limitations and these questions of uncomputability that come out of that discussion. I'm going to base most of this on this absolutely glorious little book called Computational Calculus. I've put a couple of chapters of this up as reading for this week. I hope some of you have had a look at those. This is one of my favorite books of all time, like most of the books on this module. Very excited to share it with you. And it's written deceptively in the style of a kind of A-level maths textbook. It's written in a very easy and nicely formatted tutorial style, which completely masks how revolutionary the ideas in it are. Underneath that, this is actually a manifesto. This is a manifesto for throwing out a lot of conventional ideas that the pure mathematicians have imposed on us, and then rebuilding arithmetic and calculus and mathematics in general from computation. This is about putting computable numbers as the foundation of everything, and then reconstructing most of mathematics from that alternative definition. And it's about putting computer science there as the foundation of mathematics. So, yeah, I just found it in the Oxford Bodleian Library once when I was looking for something else. Started reading it, and very addictive, very beautiful. Part of that addiction is coming from the constructive aspect of it. When you, as computer scientists, like to build things, we like stuff that actually works and that can be implemented, and it's about turning mathematics into something like that, something that can be run as a program rather than just thought about. Okay, so let's give first of all a sketch of these ideas. This isn't the full definition, this is to give you some intuition for what we're trying to do. When I teach junior school children Scratch, one of the exercises we do is to try and move Scratch the cat to a particular point. So you can make up little games where there's a coin or apple or something on the screen, and the aim of the game is to get your cat to land at that point. Yeah, then you score some points or whatever in the game. Now, let's take this idea. Has everyone programmed in Scratch? Have you all written little things like this?
I spent like
Never.
5 years developing in Scratch.
Okay, cool. So I'm going to share my screen and take a look at one of these little programs. Now, here is Scratch the Cat, and here is a meter stick. Okay, and I'm going to pick a point somewhere along that meter stick, and I'm going to make Scratch the Cat go towards that point. Okay, so look, I'm going to run my program. It's got a little weight in there, so you can see him moving around once every second. And can you see he starts off making quite large jumps, and this is a loop. Every time we go around the loop, the step size gets a little bit smaller, and he's actually homing in on a particular point right here. So maybe just take a minute to look at this program, and can anyone explain what this program actually does, and preferably where it ends up? Where is Scratch the Cat actually going to on that meter stick?
It looks like what the code will do is you have a variable d which will be different, or well, either different or just different. And what it will do is it will run 100 times, and each time it will change x by the value stored in difference. So at the first step, it will take x and add 100, and then it will divide d by 2 and multiply by -1 and repeat. And so every second it will move Scratch back and forth, and each time the amount it's moving back or forth is halved.
Yeah, that's it. So yeah, D is how far he moves on each step, isn't it? And D is getting smaller and smaller, and it's giving you that kind of oscillation. Yeah, he goes a little bit too far, then corrects and comes back and homes in on a particular point. Okay, so any idea where this actually lands? So he started at 0, and the first step, the 0 was this end of the ruler. He goes to 100 at the other end, and then D progressively halves, and he oscillates to a point.
Is it 2/3 of 100?
It is. So you can actually see this is rounded up because Scratch uses integer pixels. Yeah, he's landed up on something like 66.666. Yeah, 2/3 of the ruler. Good. If this wasn't rounded up, what would it actually say?
It would be, well, I
If
won't
it's
calculate it to 100 iterations to tell you the specific approximation that it gives, but it's going to be 66 point enough sixes to approximate 6 recurring.
Yeah, right. So when that number is actually calculated on the computer, it's never going to be the precise 2/3, right? It's always going to be 6.66666 and then stop. Okay. Any attempt to write that number down in decimal, at least, or binary, I guess, would have to be cut off at some point. Now,
you could be
what's
writing
interesting,
sixes until the end of the universe and still not be accurate.
right, you can keep going for as long as you want. Now, what's interesting then is that we have defined a unique point in space by this program. Okay, this program is an object in itself. If you wrote this out in ASCII, you could view it as a great big number in base 256 with a finite length. So this program is a perfect descriptor of this point. Now, when you execute the program, all you can do in practice is run it for some number of steps. Okay, so instead of writing 100 here, let's write k. Let's say you're going to repeat this thing k times. If you make this into a function of k, what you now have is a perfect description of that point, and you give it to your user, and they can choose whatever k they want, and they can obtain a k accuracy estimate of the point that we actually intend. But rather than thinking about the point, you can just think about the program. You can view this program as the number, right? This is the number, and we can operate on this number using laws of arithmetic, just as we could operate on a string of digits. When we do 12 plus 13, there are rules for taking those symbols, the 1 and the 1 and the 2 and the 3, and combining them in certain ways to get the answer. And we can do the same notion of arithmetic by taking this program. It's just a string of symbols, and manipulating it together with other programs to get programs that come out as a result. So there's a duality here. The program is the sense of the number. It's telling you how to get somewhere. It's a precise set of instructions. Whereas this point in space, this is a reference or a referent of the number. And this is like the model theory. It's telling you what the program is actually going to get mapped onto in some form of reality that the program is trying to talk about. So that's Scratch. Okay, let's make this a little more grown up. This is still just a sketch though. Let's take the same program in Scratch and we'll just write it out in Python. Doing exactly the same thing. Right, we start at 0, start with d as 100. We're going to go around the loop. This time it's clearly a function of k, so the user of this can choose whatever k they want, and the bigger k you put in, the better accuracy you're going to get. And what you'll see from this then is that as we call it with different values of k, it starts off being completely useless. 100, 50, 75. After a few iterations, this is probably good enough for many applications, like if you were writing a game with the sprites. After 10 or 20 iterations, you're seeing 6 point lots of sixes. And again, this program is an integer written in base 256. Every symbol here is a digit in base 256 ASCII. And so when we view this, it's just a number. This integer is describing this computable number. Okay, going beyond the sketch, and to do this properly, we need to add a couple of extra details to make this work. You could imagine this going wrong if your program just made Scratch the Cat fly around all over the screen and not home in anywhere. So what we really want to say is that for a program to be considered as a computable number, it has to have this property of convergence. It has to have the property that there's somewhere in space that the cat is actually on the way to. And he's not just going to oscillate all over the place and never get anywhere. So mathematically, we can do that by adding an interval to each point. We're going to think of this notation describes an interval on a line. Okay, let's take the real number line. Here's 0, 1, 2. So consider the interval 1.5 plus or minus 1. Okay, the interval 1.5 plus or minus 1 is this whole area. It's this whole area of the number line. So when we write this notation, you're describing a region of space, one-dimensional space. So to enforce this idea of the cat homing in on a point, what we're going to say is that as you go step by step, those intervals have to do two things. First of all, they've got to get smaller. I'm saying every step's interval is going to be smaller than the previous one, but they've also got to contain each other. So here, when you're on step 4, your interval from step 4 must be fully contained in step 1 and in step 2 and in step 3. Okay, so every interval is a subset of the one before it, and basically they're getting smaller. So this condition expresses that every interval is contained in the previous ones. This is a mathematician's notion of things getting smaller. Okay, you'll see this in pure mathematics, in classical analysis. It says for any value of d, you can pick whatever distance you like, and you can always find a k so that the error is smaller than d. Okay, so if you're interested in this point and you're saying I want an interval that is no wider than this, that's my tolerance of the aeroplane wing that I'm building or whatever. You know, I need my estimate to be at least this accurate. It's saying you can always find a k to make that size small enough, no matter how small this is asked for. So this thing says, yeah, it says for any d that is a rational number, remember q is the rationals, a over b, you can give me a rational number and I will find you a k so that the error of that kth step is less than what you asked for. So when you put these two conditions together, they describe the behavior we just saw in Scratch the Cat. They basically say that there's a number line and Scratch the Cat is going to wiggle around and home in towards a point of space. Oh, and importantly, the program has to halt. Okay? If your program doesn't halt for any value of k, then it isn't describing a number anymore. It's a useless program. What do we know about programs halting?
We can't say whether or not it halts.
Yeah. So if I give you a number if I give you a program like this that is purporting to be a number, you may in some cases have difficulty deciding whether or not it actually is one, because it's a requirement that it halts. So in a case like this, it obviously will halt for a particular k. So you could prove that using the rules of verification that we've seen here. In particular, this is a for loop, and there's a variant I, and it's going to get to the end of that for loop when it reaches k. You know, if it had a while loop in it, then things could get more difficult. So this program, it's another version of what Scratch the Cat was doing, but we are now going to add this error estimate. And we're going to return not only the current value of x, but also the width of that interval. So you call it with k, you say, I want the fifth accurate approximation of where we're going, the fifth one in that sequence. And it's going to give me x, and it's going to give me that interval. So it will run that thing 5 times, and the interval will get smaller and smaller and smaller, and you're going to end up reporting, here's x, and here's the width, e, of the interval. So these are really just technical conditions. They're there to make sure that Scratch the Cat doesn't oscillate all over the place. They're just saying that there has to be a point in space that he's actually headed for. But the real point is that a computable number is a function. It takes an integer, k, and it gives you the kth approximation of where you're going. And then you view the program as a whole as the number. Okay, so this is a description of that number written in base 256 ASCII. So, for example, if we run this program, you can try this in Python. Very easy to make little number functions, or you could try it in LAClecture11a. This number would just be lambda k that returns something using k. And then call it with different values of k, and there's where Scratch the Cat started off. So this time, as well as going all the way to the end of that meter stick, you've got this plus or minus 50. You're saying, you know, I've gone all the way over here, but I don't really know where I'm going. I could be going anywhere in this large interval. You know, I'm actually going to end up there at 66.666, etc. And you can see we've been quite careful in how we chose E, because you have to come up with an E that guarantees that your target is always in the interval. So it turns out in this case you can pick the absolute value of D as your error. But in some cases you have to be quite clever in coming up with a suitable E. So you'll see at each step E is reducing, and this interval is always containing the point that is 2/3. Okay, and when we get down here, you see the errors become very small, and we've got lots of 6s. Let's look at a more interesting number. It's normally done with pi, but pi isn't cool anymore now. It's all about tau. Tau is defined as 2 pi, and we argued about this when we were students. Probably every generation has done. Pi is incorrectly defined. It should always have been twice as big. It makes calculus a lot easier if you use tau instead of pi. I think this year, for the first time, there's become an organized hipster movement to actually do something about this. So Tau Day is now defined as June the 28th, and they're going to do all the things that people used to do on Pi Day, but on Tau Day. So you can buy t-shirts with Tau on it and so on. And it's called Tau because if you do Tau divided by 1, it looks like the symbol Tau. But if you do Tau divided by 2, then it sort of looks like pi. Okay. Anyway, it's an interesting example of a computable number. Right, here's the value tau, 6.283. Let's come up with a short program for computing tau, or depending on your point of view, a short program that is tau. Okay, so here's another piece of Python. Tau is a very pretty number, so it has this very elegant and short description. If it was written in a different language, it would almost be shorter than trying to write down a bunch of decimal places of it. But this contains all the information you need to compute as many digits of tau as you like. And you notice again, we're going to make sure that this error function exists, and we're always going to return x along with the error function. And again, that is just to guarantee that the thing actually converges to a point. Again, we can make some evaluations of it. We start off with this terrible estimate that it's 8 plus or minus 8, which isn't very helpful. After 10 iterations, we've got the 6 looking okay. After 100 iterations, we've got 6.2. After 10,000 iterations, we've got the first few digits correct. Okay. So this number can look very complicated. It goes on forever, but it's actually not very complex because you can describe it using this very short program. This shows you the real structure of the number. And once again, this program is just a great big number written in base 256. You can just look at it and it's the number written in ASCII. One of the problems we get in most number systems is that there are multiple ways of writing individual numbers. So at primary school you learn that this number is the same thing as this number. In this case, the symbol just means they're two different words that are describing or pointing at the same concept. You're not even doing maths here. You're just writing the thing down in two different ways. Right? If you write it down as 0.5, you learn that these are just different notations for the same thing. So we're very used to the idea that one number can have multiple ways of writing it down. Less obviously if you find numbers like this, and importantly with the dots. If these two numbers are equivalent, they're not just approximately equal, they're exactly the same number. So people often get this wrong. People often think that this number may be a little bit smaller than this number, but they're not. They're two notations for exactly the same number. So you will find this idea with programs as well. The program we've just seen computes this number, 2/3. But you can do this as an exercise if you like. It's very easy to come up with other programs that will also take you to that same point in space. So you're going to end up with two different Python programs, and they're both the same. They're not syntactically equal, but they're describing the same number in just the same way that this symbol and this symbol are describing the same number. But when you do it with programs, they can look very, very different. And demonstrating that two programs actually represent the same number is going to be quite tricky. And in fact, uncomputable in the general case. If you read the Aberth book or bits of it, or any of this literature, you will see there are equivalent definitions of computable numbers. You can prove they're all equivalent to each other, and then other proofs and arguments that are made will naturally be easier in one form than in another. So the version we've seen of this definition is called the K definition. Right, so we've just seen a number is a function, a lambda function, if you like. It takes integer k and it returns x and e subject to this convergence property. Right, these are the same equations we just saw that basically say the cat has to wobble around and move towards a particular place. So it will turn out that this is equivalent to these other definitions. Okay, you will sometimes see the number defined like this. Here, it's defined again as a function of an integer, but in this case, the integer is called d, the decimal. And in this definition, you're saying, give me d places of accuracy. So you see, this number has 1, 2, 3, 4, 5, 6 digits of accuracy. So in this case, you're saying, here's my program, it defines pi or tau or whatever. The user comes along and says, give me 6 decimal places of pi or tau. Okay, it's having exactly the correct decimal digits after the point. So it turns out this is equivalent to just choosing a particular value for k and mapping it onto each d. You could equally well do that with binary. You could say a number is a function which takes an integer b and returns b binary digits or bits after the decimal place. Give me 1, 2, 3, 4, 5, 6, 7, 8 binary digits of accuracy. So these are fairly obviously related to each other and therefore back to k. And the other one that is most closely related to what pure mathematicians do is called the E definition, E for error. So in this case, again, you have a function which takes an integer and returns an interval, as in all these cases. But in this case, the user is going to specify how much error they would like to have. So if you've got your number line, the user says, I want an interval that is at most this wide. And basically, you're going to go off and you're going to choose a k to give you enough accuracy. So k equals 1 might give you here, k equals 2 gives you here. Keep going, you get to k equals 10, and that's the k you need to obtain the E that was asked for. So if you're interested to see why this is the case, you can look it up in Abirth, but I'm just going to tell you it's the case for now. And having those different definitions around makes a bunch of other stuff a lot easier, because you can just pick the definition that fits the problem that you're working on. Right, once we have this notion of what computable numbers are, they're programs that take you to a point in space. We can then start doing arithmetic on those numbers. As you do with regular arithmetic, you have a bunch of rules for manipulating symbols. It's just that in regular arithmetic, the symbols are digits, and you have the rules you learn at primary school for adding columns together. In this case, the symbols are ASCII base 256 digits, and adding 2 numbers together now means adding 2 programs together. We have to define what it means to add 2 programs together. Before we add 2 programs together, let's think of a slightly easier case, which is interval arithmetic. Now, you may have seen this before if you're dealing with statistics and error functions. Forget about computable numbers for a moment, and let's just consider 2 intervals. Okay, here's my number line. And if I know that x is somewhere in here, and y is somewhere in here, what does it mean to add these 2 intervals together? So, for example, if there's two people and we know their heights plus or minus 1 centimeter, okay? Person 1 is 1.7 meters plus or minus 1, and person 2 might be 1.8 meters plus or minus 2. Sorry, that's 2 centimeters. Just put in cm. That's centimeters. That's meters. Right. If we get person 1 and person 2 and we stand them on top of one another, what is the total height? I'll write this down. Let's write the whole thing down in centimeters. Actually, makes it easier. Plus or minus 1 centimeter. Right. Person 2 is, what did we say? 180 centimeters. Plus or minus 2 centimeters. Okay. So if we stack those 2 people on top of each other, what is their total heights?
Would you like an answer?
Yeah.
Is this a hypothetical question? Okay.
No, I'd like an answer.
It's 350 plus or minus 3 centimeters.
Plus or minus 3. Good. Good. So the point is we define the two heights as intervals, okay? And we have a rule for how we do addition on intervals. Normally addition is defined on integers or rationals or other kinds of numbers. Here we're defining what it means to do addition on these other kinds of things called intervals. Yeah, so absolutely. Addition's easy. You add the two x's together and you also add the two errors together. So that 3 has come from adding this one and this one. What would we get if we multiplied their heights together?
You asking us to do arithmetic? This is terrifying. I chose computer science so I can let computers do arithmetic for me.
Yeah, cool. You can do it in Python. Okay, it's the same kind of idea. It's a little more complex because the way the errors combine, you have to think through the logic. If you think through the logic, you'll come up with this. You'll see you multiply the main numbers together, and then rather than adding the errors, you do this other thing. There's a different way of combining the errors. Okay. If you were to subtract them, then you would add the errors in just the same way as when you do addition. Division is harder because it can go wrong. Division is not a fully defined operation because you have this problem of division by 0. And when you take that to intervals, there are some intervals that could contain 0 or could make your calculation end up in a division by 0. So for division, you actually end up with two rules together, and you say if things are behaving well, then you do this. If you do the main division, you do a thing to the errors. But if this is exactly the problem you get in floating point arithmetic that makes your Mars rovers explode. If your number is very small compared to the errors, then you have a problem and you just can't give an answer. So the reason we're interested in...
where has m popped out of in this bottom one? How do we calculate m?
That should be x, shouldn't it? Yeah, they're called x here. Sorry.
Yeah.
x2. Good, good, well spotted. I think in our birth, m looks there as well. That should be it. Okay, good, good. I'll fix it on the side. Okay, so the reason we're interested in interval arithmetic is because when we do computable numbers, they're defined as these functions that spit out intervals. And so to do arithmetic on computable numbers, we're going to have to base that off of arithmetic on intervals. There's a whole bunch of these m's and x's. Okay, m's and x's are the same thing again, right? As well as plus minus times multiply, we also need to define equality and inequality. So what does it mean for two intervals to be equal? So pure equality means they're exactly the same interval. They're the same set of points on the number line. But it is also useful to consider this operation. This is called dotted equality or interval equality, maybe. This symbol means that there's some overlap between the intervals. So look, these two intervals do not overlap. Interval A is clearly less than interval B. And that's what we're defining here. This is interval A is definitely less than B. But there are multiple ways that they can overlap. Okay, they can overlap like this, or one can be smaller than the other, or the one can be bigger than the other. And in all of these cases, we're going to write A dotted equals B to show that the intervals are overlapping, which roughly means they're equal, right? It's saying that if A and B were describing numbers, there's at least some chance that they could be exactly the same number, whereas in this case, they're different, because A is very definitely less than B. So you can write those using logic rules again. These are the names of the rules, little comments as always, and you're introducing the symbol. You're saying you're allowed to write this if and only you can prove this other stuff. Question?
Not super a question, but I think it's remarkable that the first time that we've really gone in depth in something like intervals and error is in logic and computation, as opposed to because I've heard physicists and engineers and such say something along the lines of, if you don't provide error to a measurement, the measurement is completely useless and of no help to anyone. So I really feel like you can measure the degree of actual real world insistence and usefulness by the existence of things like this. It's
2 weeks before you finish your degree, isn't it? Are any of you thinking of going into careers making aircraft and nuclear power stations in a few months?
Yeah,
that's might be good to know about some of this stuff.
Yeah. Oh dear.
Okay, so we nearly have all the ingredients now to do arithmetic on Turing's computable numbers. So instead of spelling these all out one at a time, we're not going to define addition and subtraction and multiplication, blah, 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 for computable numbers individually. Let's do the whole lot at once with a bit of Lambda style notation. This is just being lazy, less typing on the slide. Let's define a function which creates new computable number operators from rational ones. Okay, so if you've got any operator on rational numbers called O for operator, such as addition or subtraction, if you give me that operator, I'm going to turn it into a computable number version. Okay, and I'm going to do it using this lambda expression here. So roughly L for lifting, I think. Lifting means taking something out of one domain and putting it in another one. So this operator, it's a lambda function. It's going to take your operator, which might be addition, right? Then it's going to take two computable numbers, T for Turing. Yeah, and remember those things are programs. They're little functions of integer k. It's going to take your operator. It's going to take two Turing computable numbers, and it's going to take a new k, and it's going to give you back this. It's going to apply the operator to the two numbers as functions of k. So that's actually really bad teaching, because I've showed you a massively abstract thing before I showed you the example, and we're supposed to show the examples first. But it's a clever way to define it. Let's look at the example second, and that actually makes sense. So for example, let's apply this lifting operator to addition. Okay, I'm going to define a new operator called computable number addition. So it's add Turing to computable number. And I'm going to get it from applying my fancy L thing to good old-fashioned rational number addition. Okay, so when I plug that in, if I apply this whole L thing to addition, and remember we saw how to define addition a long time ago now. When we plug that in, we're going to get this new operation coming back here. And this is the operation that takes two Turing computable numbers, and that should be a k, that's a typo. It takes two Turing computable numbers and an integer k, and it returns this. It's going to compute the kth approximation of each Turing number, and it's going to add them together. Including adding the intervals that come out of those Turing numbers, as we just learned how to do, adding the e's together along with the x's. So that's how you lift all the operators into computable numbers. You can make division and exponentiation and everything you like with versions of that. Technically, this is only for operators taking two arguments, but you can do similar. And then you have to define equality for computable numbers if you want to do anything interesting arithmetically. And this is going to be quite tricky. It's easy to say what you want, but it's hard to actually prove when it's taking place. We're going to define Turing computable number 1 equals Turing computable number 2 if for every possible value of d, all the digits of Turing number 1 are the same as all the digits of Turing number 2. Okay? And look, that's that dotted equality operator. You're saying these two intervals intersect somewhere. So this is kind of tricky, right? Because you have to prove something is true for all d, and there are potentially infinitely many d's. So you're not going to be able to check them one at a time. You're going to have to actually prove stuff. But conceptually, two numbers are equal if they are two programs that produce the same list of decimal place values. Okay, so what does that actually look like in practice then? It means when you're going to... David.
Sorry, I had to reload the Collaborate Ultra thing because of I don't have access to the code for the workshop anymore.
Okay.
Go to.
You're heading out and coming back in again.
I had to drop out because of yeah. So can we put the codes back in for chat?
The codes, yeah. Hang on one sec. There we go. Good.
Cheers.
Okay, so in practice then, this is what it can look like when you add two numbers together. So here I'm going to add, my number is the thing I defined for Scratch the Cat, right? My number is 2/3, and we saw the program for it. And this is tau, remember? Tau is 2 times pi. So here I'm going to do an addition. I'm going to add 2/3 to tau. And remember, my number is just a great big ASCII string, and so is tau. And the result of that addition is this thing, right? The result of that addition is a new program. Not quite sure what language this is supposed to be. Some kind of bastard child of Python and lambda calculus, I think. But the result of this is you've got a function. You get a new function that also takes integer k. And this stuff has come from 2/3. This has come from my number, and this stuff has come from tau. And the new program has got text from both of the two input programs. It's going to go and call them each with a value of k that you've put in. It's going to go off and evaluate it k times. It's going to figure out how to do the addition here. So look, here's the rule for adding intervals. So interval addition just means you add x's together and you add the e's together. So creating this addition operator for computable numbers is roughly concatenating two programs together, calling them both with the same letter k, the same number k, and then doing interval arithmetic on whatever comes back. So you can then say things like this, yeah, I'm going to compute this number plus my number, that should be tau, that's a typo. Add my number to tau and approximate the result to k is 100 steps, and there's your answer to a precision of k equals 100. Okay, you can see this thing comes out naturally as a curried function. That's one function call, and it returns a lambda function of k, and then I've called it again with a particular k to actually get a numerical approximation coming out. So you can kind of imagine how to scale this up, right? You could create these functions for multiplication, for exponentiation, and so on, all your favorite maths operators. What's the problem you will very quickly run into? What's going to happen if I do 10 of these additions?
I mean, like in a real sense, although abstractly they compose properly, and the composability works for as many different kinds of function as you'd like. The problem is that now we're calculating this 100 iterations, for example, say 10 times. So it scales it scales hard.
So yeah, you know, say I just add the numbers from 1 to 10 together. You know, how big is the resulting program going to be? You know, how about if I just add 10 of these towers and stuff together?
Well, I mean,
you know,
the space complexity, I think, like, if I think about it like really abstractly, the space complexity of the program isn't going to change that much. I think the main problem is like in the time complexity difference, right?
Mm-hmm. Okay, but yeah, it's going to grow, right? When you add on a calculator, if you do tau plus tau plus tau plus tau plus tau, you've still got 12 digits of calculator display that is the same size thing that you had in a single tau. But yeah, this one way or another, this is going to grow. Every time you do some arithmetic, your program gets longer and longer. So you imagine doing this over time, right? Imagine you're running the Mars rover, and every 10th of a second it has to add a temperature measurement in or something to the average. And these things are going to get bigger and bigger. Now, if you did add all the numbers from 1 to 10 together, which would give you 55, yeah, 10 plus 1 all times 5. You can, as a human, come up with a much simpler program that represents that same result in a much more efficient way, such as a program that just prints out the number 55. So what you really need now is an optimizing compiler. You need a magical compiler that can take your 100 pages of concatenated together maths functions and say, oh, that's actually just the number 55. So let's replace all that code with an optimized version of that program that just prints out the number 55. Wouldn't it be nice if we had a perfect optimizing compiler that could actually understand everything your program was doing and make it into the shortest or fastest possible variant of it? Sounds a bit too good to be true, yeah? And it will be. But we could at least imagine doing this. We could imagine defining all those mathematical operators that are acting on the programs. You know, as your primary school arithmetic acts on strings of digits, so these functions act on strings of ASCII. You know, they're adding programs together, they're multiplying programs together, doing all of those operations to reconstruct the arithmetic that we know and love. Should we take a break for 10 minutes?
Sounds good.
Let's come back at 3:32. See you then.